Hello everyone and welcome back to my channel. In today's video we are going to deep dive into one of the most important building blocks of every microcontroller, the clocking system. I will be using the TI C2000 F280049C as an example to show you both the theory and the practical configuration. In the first part, I will explain the fundamentals, why every MCU needs a clock, what the simplified C2000 clocking structure looks like, how the PLL works, and how the system and peripheral clock dividers are derived. We will also go through a step-by-step frequency calculation example so you understand exactly how your MCU runs internally. In the second part, we will move into practice. I will open Code Composer Studio and demonstrate how to configure both internal and external oscillators. So you can see how this theory applies on real hardware. This video combines two full lessons from my C2000 Basic course, so you will get a real taste of how I teach inside the course, step by step, practical, and focused on real world applications. So let's get started with the theory part. Let's begin by talking about why the clocking system is so important in a microcontroller. Every microcontroller, including the C2000, needs a timing reference. This is the clock. Think of the clock as the heartbeat of the device. Just like our heartbeat sets the rhythm for our body, the system clock sets the rhythm for everything the microcontroller does. The first and most obvious role of the clock is that it defines the CPU instruction execution speed. If the CPU clock runs at 100 MHz, that means at best it can execute 100 million basic operations per second. Without this timing reference, the CPU simply wouldn't know when to perform the next instruction. But it doesn't stop with the CPU. The same clock also drives the peripherals. That includes communication modules like SPI or UART, timers, PWM generators, and even the ADC. Each of these peripherals relies on precise clock signals to function correctly. For example, the baud rate of a UART is directly derived from the system clock. If the clock is off, your communication link won't work properly. Now, why is this especially important in digital power control? Because timing accuracy directly impacts system stability and performance. Let me give you a few examples. The ADC must sample at the right moment within the PWM cycle to capture accurate voltage or current feedback. If the sampling is delayed or inconsistent, your control algorithm will receive wrong data. The PWM signals that drive the power stage must switch with precise frequency and duty cycle. Even small deviation can cause efficiency losses or generate unwanted harmonics. And finally, the interrupt service routines, where most of the control code runs, depend on a stable and predictable clock. If interrupt timing drifts, your control loop will not execute at the intended frequency, and that can destabilize the entire system. So, to summarize this motivation, the clocking system is not just a background detail of the C2000, it is the foundation for everything from CPU performance to peripheral accuracy to the stability of digital control loops. That's why we are dedicating this lesson to understand it. Let's look at the simplified clocking structure of the F280049C. At the front, we have the clock source selector. This block chooses which clock source the device will use. We will see the options for that on the next slide. The selected input is then sent into the PLL or phase-locked loop. The PLL multiplies or divides the reference frequency to generate a much higher internal clock. Next comes the system clock divider. Even if the PLL produces a higher frequency, the divider ensures that the final system clock does not exceed the maximum device specification of 100 MHz. System clock is then distributed to the CPU and to the peripherals. The CPU usually runs directly at system clock, while peripherals like PVM, ADC, SPI, and UART often use additional dividers to generate their required clock frequencies. On the next slide, we will open up the clock source selector and look at the actual clock sources available. Let's begin by looking at the clock sources available in the F280049C device. Before we configure the PLL or talk about distribution, it's important to know what raw clock signals the microcontroller can use. The F280049C supports four main clock sources: internal oscillator 1, internal oscillator 2, which is default by the device, external crystal oscillator, and external clock input. Internal oscillator 1. This is a built-in oscillator that runs at about 10 MHz nominal. Its accuracy is not very high, around plus minus 10%, but it can be trimmed by software. The key point is that internal oscillator 1 is always powered and can serve as a safe fallback clock. It's mainly used as a low accuracy, quick startup source. Internal oscillator 2. This oscillator is also 10 MHz nominal with similar accuracy. The important difference is that internal oscillator is the default boot source after reset. That means when the device powers up, it runs from internal oscillator 2. Later, software can switch to another clock source. It can also be powered down in low power modes if needed. External crystal oscillator. This is the most common choice for stable operation. It is connected to the X1 and X2 pins. On the launchpad, you will typically find a 20 MHz crystal. The supported frequency range is about 4 MHz to 20 MHz, which you can confirm in the datasheet. Compared to the internal oscillators, the crystal is far more accurate, typically plus minus 50 to plus minus 100 ppm, depending on the quality. That level of accuracy makes it essential for communication peripherals and for running the PLL reliably. Next option is external clock input. Instead of a crystal, you can feed an external clock signal directly into the MCU on the X clock in pin. The maximum supported input frequency is about 60 MHz. This is useful if your system already has a master clock source that you want the MCU to synchronize with. The internal oscillators are convenient but not precise enough for high-speed communication or frequency-sensitive control. For reliable and accurate operations, especially in digital power control, the external crystal is the recommended choice. When using the PLL, you must follow the datasheet specifications for input frequency ranges, whether you are using a crystal or an external clock input pin. So to summarize, the F280049C gives us flexibility. We start with the internal oscillator for quick boot, but for precise and reliable system operation, especially in digital power control, we almost always switch to an external crystal as the PLL reference. In the simplified clocking system, we highlighted the PLL block. Now let's zoom in and look at how the PLL is structured inside the F280049C. At the input, we have oscillator clock, which comes from the clock source selector. This could be an internal oscillator, an external crystal, or the external clock in pin. Inside the PLL, the first important element is NF, the multiplier. This block multiplies the input frequency, scaling it up to generate the voltage controlled oscillator frequency, or VCO frequency. The equation is straightforward and shown on slide. The VCO must always operate within the valid range specified in the datasheet. For the F280049C, that range is roughly a few hundred megahertz, and staying within it is essential for the PLL to lock correctly. The next block is ODIV, the output divider. This divides the VCO frequency down to produce the signal called PLL raw clock. PLL raw clock is the direct output of the PLL. Just like the VCO, PLL raw clock also has defined limits in the datasheet. It cannot exceed a certain maximum value because this is the frequency that directly feeds the system clock divider and downstream logic. If PLL raw clock is outside of its valid range, the system clock chain will not operate correctly. Let's now open the datasheet and see where we can find those limit values for our clock frequencies for F280049C device. On this link, you can find the informations connected to the F280049C microcontroller. Here you can find the PDF for datasheet. Here you can find the reference manual, and here you can find the errata document. And down you can find some more examples or documents for the specific microcontroller. So we will open the datasheet, and inside the datasheet, if we scroll down to the page 85, then we can find here some informations. And as you can see, first information is that for our external clock, here are the limit clock frequencies which we can select. So minimum 10 megahertz and the maximum is 20 megahertz. Then if we scroll down here, here are internal clock frequencies limitations, what we talked about. You can see that system clock can be any value between 2 and 100 megahertz. Then for the voltage controlled oscillator before output divider, frequency which is allowed is between the 120 and 400 megahertz. Then the PLL raw clock frequency can be value inside 15 and 200 megahertz. And we have PLL system clock frequency can be any value between 2 and 100 megahertz. So keep in mind this limitation exists, and you can find it inside the datasheet. On the next slide, we will see how the PLL output signal goes through the system clock divider to generate the final system clock, which drives the CPU and peripherals. Now that we have seen how a raw PLL clock is generated, the next step is to see how it is distributed inside the device using clock dividers. The first stage is the system clock divider. This divider scales PLL raw clock down to produce system clock, which is the main system clock driving the CPU and many peripherals. On the F280049C, system clock must always be 100 MHz or below, which is the maximum operating frequency of the device. The divider is controlled by the PLL sysclockdiv field in the clock configuration registers, and it can be configured to divide by 1, 2, 4, 6, 8, etc. up to 126. From system clock, we derive the low-speed peripheral clock, or LSP clock. This is set using the LSP clock div field. LSP clock feeds slower communication peripherals, such as UART and SPI. The allowed divider values are 1, 2, 4, 6, 8, 10, 12, or 14. This ensures that these peripherals operate within their safe frequency ranges and comply with protocol timing requirements. In addition, some high-speed modules have their own dedicated peripheral drivers. For example, the PVM module often uses a system clock divided by 2 for its time-based counter, while the ADC requires a prescaler since the converter cannot directly operate at system clock speed. We will cover these peripheral specific dividers later when we look more closely at modules like PVM and ADC. The key takeaway here is that by understanding these divider stages, you can correctly configure communication baud rates, ADC sampling rates, and PVM resolutions, while keeping all clocks within their specified limits. Let's now look at a calculation example for F280049C device. Let's wrap up this lesson with two concrete PLL configurations and check the numbers step by step. We will use the same equations we introduced earlier to calculate the VCO frequency, the PLL row clock frequency, the system clock frequency, and finally the low speed peripheral clock frequency. Here are the expressions. Here is also a table comparing two example configurations, one using the internal oscillator 2 and the other using an external crystal oscillator. Let's take a look case 1 for internal oscillator. Since the internal oscillator has the relatively high tolerance, we avoid pushing it to the maximum 100 MHz. Instead, we target about 90 MHz system clock to keep around 10% margin. If we set the multiplier NF to be equal to 18, the VCO frequency becomes then 180 MHz, which is within the specified VCO range. Next, with the divider ODIV equal to 2, we get a PLL raw clock frequency equal 90 MHz. With the system clock divider equal to 1, the final system clock is also 90 MHz. Finally, if we choose LSP clock divider to be equal to 2, then low speed peripheral clock frequency is equal 45 MHz. This is a safe and practical configuration when running from internal oscillator 2. Let's now take a look case for external crystal oscillator, which is equal to 20 MHz on the LaunchPad. With an external crystal, the frequency tolerance is very small, on the order of tenths of ppm, so we can safely configure the system for the maximum supported frequency. Setting NF to be equal to 10 gives VCO frequency 200 MHz. Then with ODIV is equal to 2, we get PLL raw clock frequency equal to 100 MHz. With the system clock divider equal to 1, system clock is also then equal to 100 MHz, which is the device maximum. Finally, with LSP clock divider is equal to 2, LSP clock frequency is then equal to 50 MHz. This is the most common configuration when running the F280049C from the LaunchPad's external crystal. To summarize this lesson, every C2000 device needs a reliable clock source to define CPU and peripheral timing. We explored the simplified clocking system, the available clock sources, the PLL and frequency scaling, and the different clock dividers inside the F280049C. Finally, we walked through two practical calculation examples, one using the internal oscillator and one using the external 20 MHz crystal on the LaunchPad. Let's now switch to the practical part. In the previous theory part, we learned how the clocking system works on the C2000. Now we will move to hands-on practice using the F280049C LaunchPad board. In our last practical session, we prepared the base C2000 Code Composer Studio project skeleton. We will continue with the same project structure and now extend it with a few additional files. Specifically, we will create 4 new files: hal underscore sys, source and header file, and hal underscore gpio, source and header file. And we will put it inside the folder hal. For now, we don't have anything, and now we will just insert this. To save time, I have already prepared these files with the basic structure and oxygen comments. I will copy them into our project and then walk you through their contents. If we open hal underscore sys.h file, you will see that it already contains Doxygen documentation. Here you can see the hal system init function, and at the beginning you can see the header for our file. If we open the hal underscore system.c file, you can also see the header, and we have also some sections. For example, section for definitions, type defs, variables, function prototypes, and here for the functions. And we already have the skeleton for one function, which is hal system init function. This is where we will implement our clock initialization. We also have complete Doxygen documentation for such a function prototype, and here you can see we have the brief description, we have detailed description, pre and post conditions, return, we have for example how to use the function, and this is just history of changes. Now let's quickly check the GPIO files. You can see that it follows the same structure like we showed. The only difference is that we have here now hal GPIO init function, so different function. And if we open the hal GPIO source file, we again have the same layout. Also, we have function hal GPIO init and with its own documentation using the Doxygen comments. All right, let's return to hal underscore system.c file and configure our clock system step by step. We will demonstrate 2 different configurations, exactly as we described in the theory section. Here inside the Doxygen documentation is written as a summary what we want to show. We want first use internal oscillator 2, which is 10 megahertz, and then we calculated we need multiplier to be equal to 18 and PLL divider to be equal to 2 to have the system clock frequency 90 megahertz and low speed clock frequency we are targeting to have 45 megahertz. So this means we would need to set the low speed clock divider to be equal to 2. The same goes with external crystal oscillator, which is in our case 20 megahertz on the LaunchPad. And here we want to have frequency 100 megahertz with multiplier 10 and divider 1. And low clock speed divider will be equal, like for internal oscillator case, it will be equal to 2. We will implement both examples in code so you can clearly see how the configuration changes depending on the oscillator source. So let's get started by coding the first case, the internal oscillator configuration. To save some time, I will just paste the configuration what we need, and then we will go line by line through the code. As you can already see from the code itself, we are using the driver libraries which are provided by Texas Instruments. First function system control set clock is used to configure our clock according to our needs. Here we select what is our clock source. In our case, we said we want to have internal oscillator number 2 as our clock source. Then here we set our multiplier. We said we want to have multiplier equal to 18. uh, this is the fractional part for the multiplier. So for example, we can select 18.2025, for example. And if we don't want to have fractional part, then we just need to select number 0. So we want to have 18.0. Then we select the divider, which is number 2. And then we select the system clock divider, which we said it will be equal to 1. And here we enable the PLL. Using the function system control set low speed clock, here we select what is our prescaler value, and system clock with this configuration is 90 megahertz. And if we select the prescaler equal to 2, then we will have a low speed peripheral clock equal to 45 megahertz. To verify that our clock is configured correctly, we have an option that we put the clock signal to the external pin. And with this function system control select clock out source, we can select which clock we want to see on our pin. So we can, for example, select PLL system clock. We can select uh, other options. So for example, internal oscillator 1, 2, PLL raw clock, system clock, external oscillator clock, and so on. Additionally, we have option to divide this clock, which we will see on the pin. So, for example, in this case, if the PLL system clock is 90 megahertz, when we divide it by 2, it will be 45, and we should see on our pin 45 megahertz. Maybe for the beginning, we can just put on our pin, we can put internal oscillator 2 as shown here. On the F280049C LaunchPad, we can use GPIO 16 for this purpose. All we need to do here is configure that pin as the special function output for X clock out. Since we haven't yet talked about the general GPIO configuration, I will just show you the minimal code needed without going into details. In the next lesson, we will cover GPIOs more systematically. So then we go to hal_gpio.c file, and here I will just place the correct configuration. In short, we initialize the pin GPIO 16 as an digital output with a special function for X clock out. And that's all what we need to see the clock signal on our pin number 16. To see exactly on our launchpad where the pin 16 is connected, we need to open the official web page from the TI, where we can find documentation about the launchpad which we are using, and we just need to scroll down a little bit. And here we can find the user guide for Launchpad Development Kit. And if we open it and if we scroll it down a little bit, here is where we can find the pinout. So on the right side, right top side, you can see the booster pack, and here is where we can find GPIO number 16. It's pin number 15, so fifth from the right side, 1, 2, 3, 4, 5. So this is the pin. Now we can return back to our Code Composer studio. And before we flash our device or launchpad, first we need to go to the main.c, and here we need to call our prepared functions. We need to call our HAL system init function where our clock is initialized, and we need to call HAL GPIO init function where our GPIO is initialized. Also, we need to add includes here. System.h and GPIO.h. Now we can build our project. As you can see, project was successfully built, and let's now see our test bench. In the upper right corner of the screen, you can see our test bench. Here, channel 1 of the oscilloscope is connected directly to pin 16 of the launchpad. In the lower right corner, I've zoomed in on the oscilloscope measurement from that pin. For this demonstration, I'm using a Rigol 100 MHz oscilloscope, and the signal is displayed through the Ultrascope application, connected to the PC via USB. Now let's go ahead and flash our device and check what signal we get on GPIO pin number 16. To flash the device, we need to go here to debug. Once debug session is started, we are at the beginning of our main, and if we want just to run our device, then we just click here resume. And now you can observe that we have a signal on our GPIO pin number 16. And if we take a look, what is the frequency or the time period is equal to 200 nanoseconds, which corresponds to a frequency of 5 megahertz. If we now go to the halsys.c file, here we can see that we wanted to see on this pin internal oscillator number 2, and we wanted to see this signal divided by 2. So internal oscillator 2 was 10 megahertz, divided by 2 is 5 megahertz, what we see on the pin. Let's verify this. Let's now try to divide by 1. First we need to stop the current debug session and then start again. And project is first built, and then the new debug session is started. And then we can now click run. And you can see now the frequency is double. Now we have 100 nanoseconds, which corresponds to 10 megahertz. Okay, but we wanted to check if we correctly configured our clock. Instead of internal oscillator, let's now show what is our system clock. Because it's 90 megahertz. In our case, I would divide this by 8, and then we can just run. And now we can see the frequency is a little bit higher than 10 megahertz. If we want to see more detail, then I would need to zoom this. And here we can see it's approximately corresponds to 11.25 megahertz, which is in our case correct, because here we have 90 megahertz divided by 8. This corresponds to 11.25 megahertz. Okay, with this we confirmed that our clock is configured as expected using our internal oscillator 2 source, which was 10 megahertz on our device. Now we will add the configuration for the external crystal so the system runs at 100 megahertz. To keep both clock setups in one codebase, I will use conditional compilation, one branch for internal oscillator 2 for 90 megahertz, and one for external crystal 100 megahertz. If you are new to conditional compilation and want a deeper dive, I cover it step by step in my C programming course. Here we will add our conditionals like shown here. And we will define this macro at the beginning under the definitions. And for now we will just put it to be equal to 1. So how this works is if our define or macro is equal to 1, then this part of code will be compiled. On other hand, if it is different from 1, this part of the code will be compiled. And for us, if it is 1, it will be internal oscillator configuration. If it is 0, it will be external clock configuration. So we will for now put the 0, and then we will add the configuration for the external crystal oscillator. Let me paste the code. So here at the beginning, the difference is that we enable the crystal mode, then we enable the external crystal oscillator, or we turn on the crystal oscillator, and the rest is actually the same. The only difference is that we here select a different clock source. So instead of internal oscillator 2, we select external oscillator, and then multiplier is instead of 18, it's number 10, and divider is 1 instead of 2, and everything else is the same. Here a low speed clock divider is set to be equal to 2, and then on the external pin we want to see the system clock, which is divided by 8, so we will expect to see 100 megahertz divided by 8. This is the frequency what we will expect to see on our oscilloscope. Let's now build the project and see how it works in practice. So build was successful, and let's now flash the device. And if we run it, we can see the signal on the oscilloscope. And let's now try to see what is the frequency. So here, if I click measure, then a frequency is 25 megahertz, so period is 40 nanoseconds. But something is not okay. We can see here we are targeting for 100 megahertz. 100 divided by 8 is 12.5 megahertz. So what did we wrong? I made one mistake with the purpose so that you can see how you really test your system clock frequency. So here I inserted a divider to be equal to 1, and this divider should be equal to 2. Otherwise we have 200 megahertz, not 100 megahertz. And I will now just fix these comments. Okay. And now we can try again, and now everything should be okay. And run again. And now you can see everything is fine. We have 12.5 megahertz, approximately 80 nanoseconds time period. We can zoom out a little bit. And maybe we can also test one more time just to see the external oscillator. And then we can have here divider by 1, and let's run it again. And we can see our external oscillator is 20 megahertz as we said, and it corresponds to 50 nanoseconds. Okay, I will just return back values. That's it for this video. You have just seen how the C2000 clocking system works, from the main clock sources and PLL structure to the practical setup of internal and external oscillators on the F280049C. If you enjoyed this and want to continue learning systematically, the full C2000 Basic Course is now published on hkacademy.com. Inside the course, you will find detailed explanations, complete project files, and step by step demonstrations. Everything you need to confidently start programming C2000 microcontrollers for real time control applications. The next module, Module 5, will be available in the next 2 weeks, so this is a great time to enroll and follow along as new lessons are released. Don't forget to subscribe to the channel and turn on notifications so you don't miss upcoming C2000 tutorials and course updates. Thanks for watching and see you in the next video.